Hello guys, it's Craven Bookworm, and as sort of a part two, you could say, to the video which I created recently, at which I gave a shout out to various channels out there. In this video, I actually wanted to talk a little bit about a textbook book haul that I wanted to do. So typically, like, people will do book hauls for, let's say, new novels and new books that they found got themselves. And in my case, I did give myself some new novels. I did give myself some nice new fiction material. But in general, I want to actually mention those as I review them and as things go on. But there are some textbooks which I pretty much definitely will want to talk about in this video, as I've got myself some pretty sweet textbooks. And for me, I think the feeling of getting a textbook is very reminiscent to the video that Kyle Cabasares, I think, the video which he made right here, which you can definitely check out. It's about 40 seconds long, but summarizes my experiences with textbooks in a nutshell. One of the textbooks very nicely ties into one of the projects which I've done on this channel, and that is the textbook by Sean Carroll on the subject of general relativity. This book, Space-Time Geometry, I will say it is more daunting than some textbooks, but some can get pretty bad. Like this one's actually pretty good. The content, however, is I think it is good to jump into it after you've gone through covariant physics. So I myself have bought this book, even though some of the stuff, even from the get go, from the first chapters, is already pretty daunting because Sean Carroll uses, if you are into physics already, he uses basically the math of differential geometry to give rise to a lot of these arguments for the tensory types of, you could say, the tensor identities and such, which are constantly used in relativity. So if you didn't get what that means, don't worry. If you do, good for you. But basically, he jumps into the spicy math very early on instead of like easing you into analogies and such of space-time curvature or of what Einstein like thought of with trains and light. He jumps right into the math, which is very daunting for someone who's learning this for the first time. Hence why I'm still very happy with my covariant physics books, which I'm still working through. But I got myself this because I'm very confident that I do want to jump even more into general relativity like later on. So I think this will accompany me very nicely for further courses in GR, not even in undergraduate, but I think at the more graduate level, so at the master's level, this will really benefit me, and of course for my own personal curiosity as well, as I really like general relativity so far. So Sean Carroll's Space-Time and Geometry is one of my newer books, and one of the subjects which seems like this overarching, like this behemoth of a subject, which I really wanted to delve into in a very similar fashion Simon Clark did in his video of it. Quantum field theory, I really want to learn it, like, and I haven't even done my first quantum mechanics course yet. Like, yes, I've delved a little bit into quantum, but nothing too serious. Like, I skimmed over some chapters of the Leonard Susskind's theoretical minimum book, which is really good for quantum. And I've also watched like Sean Carroll's like biggest ideas video on quantum mechanics, which again, pretty good for like an overview, especially as it doesn't shy away from the math. And with linear algebra, it's already helping me after getting over the hurdle of Bragg notation to kind of understand the idea, at least, behind quantum mechanics, that, oh, you have this, like in linear algebra terms, you have this collection of measurements, you could say, that resides in this abstract thing called the Hilbert space. But in general, the gist of which I got with quantum mechanics is that there are two main ways of like describing quantum mechanics, and one way is the matrix mechanics way, which was devised, I think, by Heisenberg, and I think Dirac and Bohr worked on this as well. No, I think Heisenberg and like Bohr and such. I think those people worked very prominently on. I know Heisenberg especially worked on matrix mechanics, which uses a lot of linear algebra to describe stuff in quantum mechanics, which means that calculationally it's a bit less intense, but it does fail to represent some things, I think, in some regards. And there's also the wave mechanics forms, and that is the way that is a lot of times taught in on the bachelor level for physics like courses, like for example the famous quantum mechanics books for undergraduate, the DJ Griffiths book, uses mainly wave mechanics. So it introduces the Schrodinger equation, that's a wave function, and it teaches you how to do stuff with the wave function from there on. So you do have to then deal a lot with calculus, differential equations, and such. And I think both of them have their uses in general. And some of the textbooks use a combination of both. For example, the quantum mechanics book, which I own, which is not one of the new books, I've had this for some time already, but I've started to recently dabble into it. That is the Satali, yes, the Satali textbook on quantum mechanics. It uses both matrix and wave mechanic formulas in some sense, so that's kind of nice. But I know that those are two ways of looking at quantum mechanics, and I know about those things. But know also that, for example, when you want to introduce special relativity into there, it becomes more complicated and you delve into the realm of things like the Dirac equation and eventually quantum field theory. And because it is such a behemoth of a subject, and I'm also very curious as to its application when it comes to like particle physics and high energy stuff with gauge fields and some of the symmetry like things that are invoked in there. I got myself some quantum field theory books. One of them is a book that was recommended both by my advisor, so in real life, my like academic advisor, and also the Mark Weitzman's video on like the list of books that he recommends for a subject. In this case, his this video on quantum field theory, and that is the Ryder Quantum Field Theory textbook. It might not have an attractive cover, and even though some people try not to be biased as to the cover, I am kind of biased. I can't help it with the cover of the textbook. It looks very plain and simple, but I have gone through the examples of it online before getting myself a copy of the book, and I then noticed that it seems to be very readable, especially as I actually work through some quantum mechanics. Like at this point, I have a very qualitative understanding of quantum mechanics, but I don't have a very nice understanding of like quantitatively how to deal with quantum mechanics. I know all of the lingo with the bracket notation, with some of the linear algebra stuff, but I haven't done these calculations myself. So I think after I do that, after I actually get my hands dirty and actually do some of the quantum mechanics physics problems out there, then I will be a bit more comfortable to tackle something like this. Especially considering now that with relativity, I am a bit more comfortable, especially with special relativity. And soon I will be taking a course on electrodynamics as well, which will be even better because I heard that predominantly for quantum field theory, the most of what you need is actually a good solid understanding of special relativity, electromagnetism, and quantum mechanics. And I think if you have those three under your belt and, of course, are comfortable with some math, then you should be good. So I think quantum mechanics is one of those last pieces I need to put in that puzzle in order to actually be able to tackle something like quantum field theory, like this Ryder textbook. Besides the Ryder textbook, I got myself a book which I've seen already reviews of it online and it looked interesting, especially for my like personal like academic interest, and plus the cover is actually pretty nice for this one, and that is the book Quantum Fields, I think by, yes, Michael, who I'm not gonna try to pronounce that last name, but Michael, basically. Michael wrote a book with a very nice cover of quantum field theory, but also if you go through the index of this book and if you look at the chapters, some of the topics covered here are actually not covered from what I saw in other quantum field theory textbooks. Like for example, I looked at the index for the Peskin and Schroeder and also the Schwarz quantum field theory textbooks, and both of those books are way beyond anything I can imagine right now. They're really advanced books, at least for me. Calculationally very heavy. They jump very much into some of the deeper like maths, utilizing some partial differential equation solutions and stuff that I'm not even familiar with right now. But they emphasize a lot some of the particle physics applications, like especially doing calculations with Feynman diagrams. Pascal and Schroeder especially is very guilty for this, from what I saw. And quantum field theory, from what I gather, tends to be used for a lot more than just those particle physics applications. Like yes, it is a big part of it, as like a good portion of quantum field theory was discovered in order to aid like discoveries in particle physics, but Right now, it is being applied, especially in other areas like condensed matter physics as well. Though for that, you probably want an entirely different textbook, like something on many body physics. But it is also well used in cosmology a lot, and cosmology for the sake of particle physics, but it there are problems in cosmology which very much lie at that like edge where you need to utilize quantum field theory. Like one of them, the only one of which I have some idea of, but it's still a very conceptually funky like topic for me, is the topic of like topological defects in early space time of the universe. So getting things like cosmic strings, which are, it's not the strings of string theory, but it is this one dimensional string that might have come to be from the early universe due to some weird thing happening to, I think, the one of the scalar potential field that might be the Higgs field, something happening causing a topological defect, and the topological defect being like the cosmic strings. I cannot explain that any clearer because I really do not understand what's going on there, but I know that that's a big area in theoretical physics that utilizes quantum field theory on the cosmological scale. And also, when it comes to cosmology, if you're looking at something, for example, like the cosmic microwave background radiation, which is pretty much Heisenberg's uncertainty principle printed in the sky, well, quantum field theory tends to be really important because it looking at how particles are were created and destroyed in a particular era of the universe is pretty like crucial to like knowing like the ratio at which galaxies were produced in the early universe and what the content of the universe actually looks like, and why do things appear to be like non-homogeneous in our early modern day of the universe, while if you look back at the cosmic microwave background, everything seems to be evenly spread out, like it's like the static all over the sky. Basically, cosmic inflation solves this problem, but cosmic inflation itself is a big issue right now in like modern cosmology. And if you want to delve into those fields, besides knowing like general relativity, like for the whole metricy thing, you want to know some quantum field theory as well. So I think if you're interested in the edge between like quantum field theory and like cosmology, I think you would very much appreciate this book. You might want to give it a look online and decide for yourself if that is the case. And besides quantum field theory textbooks, I've heard from multiple sources way more experienced than me, such as Mark Weissman and also such as some professors from my university, that before you jump into quantum field theory, it is actually helpful to become more acquainted with a particle physics textbook that doesn't heavily emphasize on QFT yet. For that, I've gotten myself the DJ Griffith's Introduction to Particle Physics or Elementary Particles textbook, as I heard that it's, well, pretty good, and I will definitely agree. I've looked through this both before I bought it and after I bought it, and I've noticed that even without having formally delved into like quantitative calculations for quantum mechanics, this book does a pretty good job. Like it actually, I can understand a lot of it, even though I haven't done a formal course in quantum mechanics yet. It speaks qualities about this book that even with like just some understanding of basic physics and some maths, and not even the math isn't even the problem, but with some basic understanding of physics, this still reads pretty nicely. Like he talks, especially in the first few chapters, about some of the experiments which were done to discover like particles that were smaller than the nucleus of an atom, as that was one of the major breakthroughs of like particle physics. Like we thought of that when you have atoms, that electrons and the neutrons and the protons were like the most fundamental particles, but then turns out if you smash different like nuclei together, you actually get these smaller like particles in the form of these like showers, you can say, that are particle showers or however you want to call them, or jets basically, and like your particle colliders. So this book is definitely like I think a nice addition to my physics library, and I'm definitely curious to jump into it, as especially I find particle physics to be as interesting as I find like astronomy and like cosmology. So I'm very eager to jump into this, and especially as it won't require as much as, for example, something like quantum field theory. And it might be a nice segue into quantum field theory. So So who knows? So I hope you enjoyed that physics book haul. And also, if you want to see more things regarding either physics, novels, or books in general, or science in general, then feel free to let me know in the comments down below. When it comes to, for example, playlist that such as the Journey to Relativity, at the moment I don't have anything in mind. I was initially planning on maybe doing a similar playlist for example, programming, but considering that, well, I'm going to be pretty busy as the semester kickstarts again, like the second semester, I don't think I will have the time to especially figure out how to combine like recording my laptop screen with me talking and all of those things. That's going to take a lot of work, and I thought that maybe, well, I might do a playlist on quantum mechanics, like the math needed for quantum mechanics, like a journey to quantum mechanics, you could say, or just quantum mechanics itself, like the basics of quantum mechanics, or perhaps even something entirely different, like for example, after I've gone through quantum mechanics, actually dive into maybe some bits of particle physics, or some bits of classical mechanics, which I also really like talking about classical mechanics and Lagrangian. So I might actually leave that for you to decide. Like, if you're curious, like, do throw in some recommendations as to which like new journey would you like to see, and I might get to it whenever I get the, like, you could say, the energy and momentum to actually like put that and start that new playlist. So let me know what you think. And again, if you enjoyed this video, feel free to like the video, subscribe, and stay tuned for more videos. Bye.